Section 4.1, increasing, decreasing, and concavity. All right, think about algebra. Back in algebra, you learned that, okay, your function's increasing right here, and then it's decreasing here, then it starts increasing again, and so forth. And you were told to list the intervals where it's increasing and decreasing. They gave you nice, pretty functions you were able to do that easy for. Well, now we're going to look at it from a calculus point of view. And you might have subtle changes sometimes in your function and where you can't really tell by just looking at it, so you use calculus to help you out. All right, let's look at where it's increasing. Like, let's say right here where it's increasing. The slopes of my tangent line are all positive, right? How about right here? My function's increasing here. The slopes of my tangent line are all positive. They have a positive pitch. How about where my function is decreasing, like right here? The slopes of my tangent line are all negative. How about my function decreasing over here? The slopes of my tangent line are negative. It's going down the slopes. So where do those changes occur? Where my function's increasing or decreasing and increasing? Think about that for a second. Like right here, what's the slope of your tangent line there? 0. So right here we have a slope of 0, and that's where it changes from increasing and decreasing. What about right here? What is the slope of the tangent line right there? It's 0 as well, and that's where it goes from decreasing to increasing. What about right here now? What is my derivative right there? What's my slope of my tangent line right there? It's not defined, is it? But what happens? My graph goes from increasing to what? Decreasing. So where does your graph change from increasing to decreasing or vice versa? That happens where your slopes of your tangent line are 0, or where your slope of your tangent line is undefined. So what does that mean? Slopes of tangent lines, derivatives, right? So if I want to find out where my function's increasing, where it goes from increasing to decreasing, where it goes from decreasing to increasing, and so forth, I find where my derivative or slopes of my tangent line are 0 and where the slopes of my tangent line are undefined, and I work from there. All right, so let's see some examples here. First example that we have from the notes, we have find the intervals on which f of x is equal to, we'll start out with a baby function, a polynomial, 3x to the fourth minus 4x cubed minus 12x squared plus 5. Okay, here's their example. And it says, find the intervals on which this thing is increasing and where it's decreasing. Find the intervals where it's increasing first, find the intervals where it's decreasing. All right, instead of graphing this, I have a much better way of doing this, using calculus. So if I'm going to find where my function's increasing and where it's decreasing, I'm going to find out, first of all, where that change happens. Remember where that change happens? Like where it goes from increasing to decreasing? This is where the slope of my tangent line is 0, or where the slope of my tangent line is what? Undefined, right? So let's find the slope of the tangent line. Or, in this case, the slope of all the tangent lines, the derivative. What will that give me? 12x cubed minus 12x squared minus 24x, right? All right, now what I like to do next before I go any further here is I like to factor this. I can factor 12x out of each one of these terms. So I'm going to say, okay, we have 12x. If we pull that out, I'm going to have x squared minus x to the first minus a 2. Now, try to factor this as much as possible. Like, try to factor this trinomial in here. So that's 12x. And then if I factored in the two binomials, I get x, 2, 1, minus a 2, plus 1. So that's f prime of x right there. All right, now, what am I looking for? I'm looking for where the slopes of my tangent line, or my derivative, is 0 and where it's undefined. So let's take this, set it equal to, let's take this derivative, set it equal to 0. Well, we just take each factor and set it equal to 0. So 12x is equal to 0, x minus 2 is equal to 0, and x plus 1 is equal to 0. So that means x is 0, x is 2, and x is negative 1. All right, so we just found out where my derivative is equal to 0. What about where my derivative is undefined? Well, this is just a polynomial. It's not going to be undefined anywhere. All right, so what I'd like to do next is I'd like to create a number line, okay? I'd like to just draw me a number line here, and I'd like to call that number line f prime. And I want to break it up with 0, 2, and negative 1 on it. So here's 0, here's negative 1, and here's 2. Don't worry about drawing at the scale. Just put them in the correct order. All right, so what happens at 0, 2, and negative 1? What happens at these points right here? That's where my derivative is 0. That's where the slopes of my tangent line are 0. What do I want to find? I want to find where is the function increasing, where is it decreasing? Remember, my function is increasing, like in this area, where the derivative is positive, where the slopes of the tangent line are positive. And it's decreasing where the slopes of my tangent line are negative. So what I want to do is I want to check this area right here between negative infinity and negative 1. Are the slopes of my tangent line going to be positive? Because if so, my function is going to be increasing. Or in this area, are the slopes of my tangent line negative? Because that'll be where my function is decreasing. All right, so what we do is we use test values here, like pick a value in this interval and run it through your derivative to see if your slopes of your tangent line are positive or negative. Let's pick any old value in here. I'm going to pick negative 2. What if I run negative 2 through this derivative right here? Okay, evaluate this derivative, negative 2. 12 times negative 2 is what? Negative 24. So really, all I'm worried about is the sign here, okay? So that's negative 24, negative. What about in this set of parentheses? What if I pick negative 2 as my test value? Negative 2 minus 2 is a negative 4, so that becomes negative in there. What about in this set? What happens whenever I get, or I sub in a negative 2? Negative 2 plus 1 is a negative. So now, this is all multiplied, right? So what's a negative times a negative times a negative? That'll be negative right here. So if f prime is negative, then that means that f is increasing right there. Let's do the same thing here, here, and here. Let's find some test values, okay? All right, so let's use a test value in here. Maybe like a negative 1/2. And let's run it through my derivative function. Negative 1/2 times 12 gives me a negative 6, but all I care about is the negative here. Negative 1/2 minus 2 is a negative, right? Negative 1/2 plus 1 is a what? Positive. Now, if all three of these factors are being multiplied, multiply these three. What's negative times a positive? A positive here. So if f prime is positive, if my slopes of my tangent line are positive, that means that f is increasing. Actually, this should be decreasing for the negative one. So change this to decreasing right here, okay? I had the wrong thing up there. Now let's test this interval. A good test value would be 1. Sub in 1 and 2 each x in your derivative. So 12 times 1 is a positive. 1 minus 2 is a negative. 1 plus 1 is a positive. What's positive times positive? A negative. So if f prime is negative, that means that f is decreasing. Now let's pick a test value here, like let's say 3. What happens if I run 3 through my derivative? I get a positive, and a what? Positive. Positive times a positive is a positive. So f then is increasing. All right, so they want me to list the intervals where f is increasing and where it's decreasing. All right, it's decreasing right here from negative infinity to what? -1. So negative infinity to -1, it is decreasing. And for some reason, this book uses the brackets here. And Wiley Plus is going to make you use the brackets. So get in the habit of that. What happens for -1 to 0? F is what? Increasing. So for -1 to 0, f is increasing. What happens from 0 to 2? F is what? Decreasing. So from 0 to 2, f is decreasing. Now, I want to say Wiley uses the union. I have to double check that. I'm not sure what Wiley uses. Wiley does certain things at certain times. All right, anyway, what happens from 2 to infinity? My f is what? Increasing. So it's increasing also from 2 to infinity. There's the intervals where f is increasing and where f is in the intervals where f is decreasing. Let's see, what else do we have? Concavities next. Concavity. All right, so let's look at some curves. I would say this curve right here is concave up. I would say this curve right here is concave down. Concave down. So concave up, concave down. Now, roughly speaking, we say my curve holds water if it's concave up, spills water if it's concave down. But really what we want to look at is we want to look at these slopes of the tangent line. Notice where it's concave up. What happens with these slopes of my tangent line? They are increasing. They go from steep negative to not so steep negative to 0 to positive to steeper positive. So what happens with concave down? The slopes of my tangent line are doing what? They are decreasing. They go from steep positive to less steep positive to negative to steeper negative, okay? So concave up, slopes of my tangent line are increasing, or my derivative is increasing. Concave down, slopes of my tangent line are decreasing, or my derivative is decreasing. All right, so your notes, go ahead and talk more about that, and they actually formalize concave up, concave down, and so forth, okay? And then it talks about, okay, let's see how we're going to find concavity, the intervals on where your function is concave up and where it's concave down. And what we're going to do is we're going to use a second derivative to do so. So we're going to do almost exactly like we did for increasing and decreasing, but we're going to look at the second derivative, okay? All right, so in our notes, if we go to the next example, okay, actually right before the example it says, the point on f at which f changes from concave up to concave down or vice versa is called an inflection point. So what does that mean? Let's suppose you have a curve that does something like this, okay? I would say the curve is concave up right here, and I would say the curve is concave down right there. But somewhere around right here, your concavity switches from concave up to concave down. And that point right there we would call the inflection point. We call that an inflection point. Now, it has to be a point on the graph of f. So what in the world does that mean? That means your function f has to be defined at that point for it to be an inflection point. All right, so determine where f of x is equal to x to the fourth minus 4x cubed is concave up and where it's concave down. So we want to determine the intervals on where this is concave up and the intervals where it's concave down. So what I'm going to do for that is I'm going to use the second derivative. So let's take a derivative first of all. F prime of x is equal to 4x cubed minus 12x squared. Now let's look at our second derivative. F double prime of x will be 12x squared minus 24x. Now let's go ahead and factor our second derivative. So I'm going to take a 12x out of each one of these factors here, and I'm left with x minus 2, and that's my second derivative. All right, we're going to do the same thing we did for the last example, but with the second derivative. We're going to find out where the second derivative is equal to 0. So we're going to take this second derivative, set it equal to 0, and we're going to find out where it's undefined. Where is it undefined? Nowhere. It's a polynomial. So we're just going to find where it's equal to 0. So let's set each one of these factors equal to 0. 12x is equal to 0. X minus 2 is equal to 0. So x is equal to 0 and x is equal to 2. So let's draw another number line. This time I'm going to call the number line F double prime. And I'm going to put 0 and 2 on this number line. And I'm going to use test values again, just like I did last time. This interval, is my function concave up or concave down? I don't know. Let me pick a test value. All right, so let's suppose I pick a test value of -1. And I run it through the second derivative. What do I get, a positive or negative? -1 times 12 is a negative. -1 minus 2 is a negative. Negative times a negative is a positive here. So it's going to be concave up here. How about a test value from 0 to 2? 1's a good test value. So if I sub 1 into the second derivative function for x, I get a positive times a negative, which gives me a negative, so it's concave down here. How about a test value over here, like 3? I get a positive times a positive. Positive times a positive is a positive. So we say it's concave up here. Now, let's list the intervals. I'm going to abbreviate concave up and concave down. All right, so concave up from -infinity to 0, -infinity to 0, and we use strictly parentheses for concavity. And it's concave up from 2 to infinity, right? Where's it concave down? From 0 to 2. I found where it was concave up, where it was concave down. Now, what if I wanted to find my inflection points? Inflection points are what? Points on the graph of my original function where my concavity changes. My concavity changes here from up to down, and it changes here from down to up. So what are my inflection points in? Well, here's my inflection points. They're going to be, well, the x-coordinates are going to be 0 and 2, because that's where the concavity changes. And what happens whenever you substitute 0 into the original function? What do you get? An output of 0. What happens if you input 2 into the original function? That's what, 16 minus 2 cubed is what? 8 times 4 is what? 32. I can't think this morning. So we have -16. And those are my inflection points. Now, this one didn't ask for it, but I just wanted to show y'all that.